Hello everyone, this is Professor Roman. Welcome to the 14th video in my video lecture series, An Introduction to Discrete Mathematics. In this video, we are ready to start Chapter 3 of the accompanying textbook, Relations on Sets. The concept of a relation plays a central role in mathematics. We've already discussed several relations, such as the subset relation, the same size relation or same cardinality relation, and the logical equivalence relation. In this chapter, we're going to study arbitrary mathematical relations in some detail. If R is a relation from a set A to a set B, then it's customary to express the fact that an element little a in capital A is related by the relation R to an element little b in capital B by writing one of two notations. Either the ordered pair AB is an element of R, or ARB. The second notation is generally preferred when the relation is a common relation and has a specific notation associated with it. For example, this notation means that A is related to B under the equality relation. Nobody says it like that, they just say A equals B. This notation means that X is related to Y under the subset relation. And again, everyone says X is a subset of Y. And this notation means that P implies Q. So that's this form of notation here. But the first notation is the one that gives us a clue as to how to actually give a formal definition of the concept of a binary relation between sets. And here's the definition. Let A and B be non-empty sets. A binary relation from A to B is nothing more than a subset R of the Cartesian product, A cross B. In other words, it's a set of ordered pairs where the first component comes from A and the second component comes from B. A binary relation from A to itself is called a binary relation on A, and in this case the set A is called the underlying set for the relation. And here again is the notation. Its negation looks like this. Just draw a line either through the element sign or through the letter R. Just to warm up, here's a very simple and probably totally useless relation. A is the set 1, 2, 3. B is the set AB, 3. Then this set of ordered pairs is a binary relation from A to B. 1 is related to A, 1 is related to C, and 2 is related to 3. Okay. No doubt the most important relation on a set is equality. But equality is not quite as simple as you may suppose. There's some wrinkles here. So, as an example, consider these two real polynomials, 1 plus x and x plus 1. Are they equal? Well, it depends on how you define equality, and this depends on how you think of polynomials. So if you think of polynomials as real functions, as you would in calculus, for example, then P and Q, these two polynomials, are equal because they are the same function. for a given input, they produce the same output, and they have the same domain and same codomain. But if you think of polynomials as formal expressions, which you might very well do in contexts other than calculus, you are thinking of polynomials as words over an alphabet. The alphabet should include the real numbers and the arithmetic symbols that go into making up a polynomial, as well as the various powers of the variable x. So that's what we mean by a formal expression, just a sequence of symbols from an alphabet. Well, these are then quite different as formal expressions, because they're not the same words. The symbols are in a different order. Or put quite simply, P and Q are not identical. So the meaning of equality, the equality relation, depends on the context, which means it has to be defined before it can be used. There isn't one single definition that applies in all contexts. So to be a little more specific, anyone who first defines a particular set of objects, such as polynomials, and who wishes to use the concept of equality, which should be just about everybody, must define what it means to say that two elements of that set are equal. Equality could be identicality, like it is for words over an alphabet. But more often than not, it is not identicality. There's going to be some slack, you might say, some leeway in terms of when two things are equal, as it would be for polynomials when they're thought of as functions. We wouldn't distinguish between 1 plus x and x plus 1. Okay. Now, as I'm going to discuss later in this chapter, so it probably won't be in this video, it is expected that the equality relation, however it is being defined in a given situation, will satisfy three properties known as reflexivity, symmetry, and transitivity. And I'll define these properties and a few more probably in the next lecture. Okay. So you don't need to worry about that detail now. One way to clarify the issue with respect to polynomials anyway would be, for example, to define two different sets. The set P of formal symbols, formal polynomials, formal words over the alphabet I mentioned before, and the set S of polynomial functions. So formal polynomials, polynomial functions. It's the same set, but equality is different. So equality on P would be identicality. They have to be identical to be equal. And you have to take that with a little grain of salt too. I mean, if somebody writes 1 plus x in 10-point type and somebody else writes it in 12-point type, technically they're not identical. They use different, one uses more atoms than the other, but that's, you have to kind of go with the flow on stuff like that. Equality on the set S would be equality as functions. Well, nobody bothers to define two different sets with two different equalities. What you just say is you define the set of polynomials and you say equal as functions or equal as formal expressions. So you have two versions of equality, and you have to be very careful to explicitly describe which version you're talking about. Okay. So if I said to you, consider the set of polynomials, here are two polynomials that are equal, you have the right to say, well, what do you mean by equal? Do you mean equal as functions or equal as formal expressions? That's a perfectly legitimate question. If a set A has an equality relation defined on it, then you can define the diagonal relation, delta 2. The 2 because it's a binary relation on the set A, and it's given as this set of ordered pairs A and B both come from the underlying set, and A equals B. And this definition would not make sense if there was not already a notion of equality defined on the set A. And you'll find in books that this is often written in this manner: ordered pair A comma A for A in the underlying set. It's okay, but this could be misinterpreted, or let's just say interpreted, as the relation of identicality. Whatever goes here, the same exact thing goes here. And so that could lead to some misinterpretation. So probably I would suggest sticking with this first version to emphasize that there has to be a notion of equality on the set. But this is a fairly common way to write that. The set of integers has several important binary relations defined on it, other than the usual ones. You have equality, less than or equal to, greater than or equal to. We can define a binary relation R on the integers by saying that M R n, or M is related to n, if M divides n. That relation is usually denoted by a vertical bar, so you would write this and you would say M divides n. So for example, 2 divides 4, but 2 does not divide 3. This relation, of which we will speak often, is known as divisibility and not division. Division is not a relation, it's an operation. It returns a value. Relations do not return a value, except yes and no. Yes, they're related. No, they're not, if you want to think of it that way. If k is a fixed positive integer, we can define a relation S sub k, so it depends on k, by specifying that M is related to n if k divides the difference, m minus n, or n minus m. It would amount to the same thing. Another way to say this is m is related to n if m and n have the same remainder upon division by k. This is an important relation, especially in number theory, and has a special notation. It's written this way, and this is read: M is congruent to n, either mod or modulo k. So 8 is congruent to 5 mod 3 because 3 divides the difference. Same thing here. 6 is not congruent to 2 mod 3 because the difference is 4, which is not divisible by 3. This is a congruence relation, congruence modulo k. Here's another important example. Let sigma be an alphabet, and we can define several useful binary relations on the set sigma star of all words over sigma. Same length relation, shorter than relation, prefix of relation. And here's a little more particular one. If we take an element from the alphabet, little a, we can define a binary relation T sub A where W is related to U if the two words W and U have the same number of occurrences of A. Relations appear in computer science quite often. Here's a simple example. A computer program is generally made up of several components called subroutines. They can be procedures, they can be functions. Generally speaking, the control of a program, the execution of a program, can be passed from certain subroutines to certain other subroutines. It's going to depend on the scope of the subroutines, the accessibility of the subroutines. So, in short, some subroutines can call other subroutines. And this defines a flow of control binary relation on the set of subroutines. S1 is related to S2 if S1 can call S2. In a similar way, some subroutines can pass data in the form of arguments to subroutines that have parameters. And that defines a flow of data binary relation on the set of subroutines. Binary relations are, by definition, subsets of a set. They're subsets of a Cartesian product. And so, because of that, it makes sense to talk about one relation being a subset of another relation. And we'd write that in the usual way with subset notation. Oh boy, wish it didn't do that. So for instance, the equality relation E on the real numbers is a subset of the less than or equal to relation on the real numbers. Got to have the same underlying set. On the other hand, E is not a subset of the less than relation on R. So also because of the fact that relations are subsets of a universal set, a Cartesian product, we can also apply the Boolean operations to relations. We can take the unions, intersections, relative complements, and so on. And this is really quite important. One of the main uses of the Boolean operations is to identify the smallest or the largest relation on a particular underlying set that has a specific property. So you are studying relations on a set that have a specific property you're interested in. Oftentimes, I think more times than not, the interesting relations with the given property are either the smallest one, or the largest one. And so you will look to study those in particular. And for example, the smallest one is easy to find. You take the intersection of all the relations with the given property. And this will come up again later on. Now, relations on a finite set can be described using what is called a directed graph. And that consists of some points in the plane. I've drawn them as dots, black dots. It doesn't have to be in the plane, actually. These dots are called vertices. The singular of vertices is vertex, not vertice, which I frequently hear from students. They're also called nodes. Together with directed line segments, so we direct them with the arrowheads, called arcs. And the arcs don't have to be straight line segments like in this case here. So these are both separately directed graphs. Incidentally, this use of the term graph is entirely distinct from the graph of a function that you do in calculus. So totally different meaning, same word, different meaning. Now, an arc from A to B is usually denoted by an ordered pair, AB. Well, that's our connection with relations. Given a digraph, that's a shortened way to say directed graph, you have a relation. You've defined a relation on the nodes where the one node is related to another if there's an arc from the first node to the second node. Okay. And it works conversely. If you have a relation that defines a directed graph, the nodes of the graph are the elements of the underlying set. So it's a relation on a set. And the arcs of the graph are the ordered pairs from the relation. When you have an element related to itself, as is the case for V5 here in the second figure, you draw a loop. Here are some examples. They're kind of pretty pictures. Suppose A is just the set 1, 2, 3, 4. The usual equality relation has this graph. You have a node for each of the elements of the underlying set, and all you have are loops at each node. Here's the subset relation on the set of consisting of just two elements A and B. Okay. Again, the nodes are labeled with the subsets of the set S, and there are arcs indicating which subset is contained in which other subset. The divisibility relation on the set 1, 2, 3, 4, 5, 6 is shown in this graph. It takes a while to construct this. You need to figure out which of those numbers divides which other, and that gives you the various arcs. And there's a loop at each node because an integer always divides itself. If R is a relation from A to B, we can define a relation from B to A called the inverse of R, and denoted as you would expect by R inverse, simply by A R inverse B if and only if B R A. So you swap the components in the ordered pairs, exchange first and second components, or if there's a graph associated with the relation, you reverse the direction of each arc. That is the inverse relation. So for the subset relation on a set B, the inverse is the superset relation. On a set A, the inverse is a superset. The inverse for words over an alphabet, the inverse of shorter than is longer than. Logical equivalence on compound statements is its own inverse. Okay. Not logical implication, but logical equivalence. If a statement A is logically equivalent to a statement B, then B is logically equivalent to A. So that relation is its own inverse, and that's not an uncommon happening. So I'm going to conclude this section of the book by mentioning that there are other types of relations besides binary relations, and they can be extremely important. Although, in some sense, binary relations are the most useful, I guess you'd say. So here's a definition. Let A be a non-empty set. A nullary relation on A is just an element of A. A unary relation on A is just a subset of A. Binary relation, as we have seen, is a subset of the Cartesian product A cross A. Ternary relation, subset of A cross A cross A. And in general, if n is at least 1, an n-ary relation on a set A is a subset of this Cartesian product, A to the nth power. So that's the Cartesian product of A with itself n times. Okay. And you might say, well, why bother with the term nullary relation when you can just say element, or unary relation when you can just say subset? Well, there's a point to what you might think, but it depends on the context, especially in abstract algebra, where you are defining algebraic structures, vector spaces, groups, rings, fields, and other structures. You have a consistent terminology if you use unary relation, nullary, unary, and binary relations. Okay, so it's convenient, elegant, but by no means necessary. Okay. Here are some examples of relations. The set containing 0, being a subset of R, is a unary relation on R. Here again, in this context, this probably wouldn't be something you'd say unless you were making an example. The in-between relation on the real numbers is a ternary relation. A, B, C is in the relation if B lies between A and C. And if you remember the diagonal relation of size 2, you can do that with any number of elements. So you can define an n-ary relation, the nth diagonal relation. Okay. But in the future, for this course, whenever I use the term relation, it's going to mean binary relation, unless I say otherwise. Okay, that completes the section, and I think then we'll complete the video. In the next video, we'll talk about properties of relations. Remember me mentioning reflexive, symmetric, and transitive. So thank you for watching this video, and I hope to see you in the next video.